particle motion. So this is um, this is going to be applicable right now while we're doing derivatives. It's also going to be applicable later on when we look at integrals. Um, it's applicable to physics, of course, and also, interestingly enough, a lot of other fields. But when you think about the relationship of, we haven't really looked at second derivatives very much except to get them. But when you look at the relationships of um, first derivatives, second derivatives, and the function itself, it's very much related to how we look at position, velocity, and acceleration. So, um, just looking at this picture, it says Mr. Barua is playing lacrosse with his best friend himself. He's not weird, I promise. He throws a lacrosse ball straight up into the air. The height of the ball is modeled by the equation S sub t equals negative 4.9 t squared, but plus 18t plus 2, where t is the time in seconds and s is the height of the ball from the ground. So be very clear about what's important here. T is the time in seconds, s is the height of the ball from the ground. Okay, what we're going to do below is graph a velocity function based on the information of this position function. I'm going to graph acceleration. And what I want to emphasize here also is that with derivatives, if I produce first, this is really big, a quadratic, right? If I get a quadratic, the derivative of any quadratic is going to be a linear function, and the derivative of any linear function is going to be a constant function. Okay, similarly, going back up, we call it an antiderivative or integral. The cubic function produces a quadratic. The quartic function, this is a fourth degree polynomial, produces a cubic function when we're talking about derivatives. But here, we typically are staying within the areas of quadratics, linears, and constant functions. Okay, so here is my position function. It's f sub t, and we use, this is distance. We're talking about distance here, equals, and it's given to us, negative 4.9 t squared plus 18t plus 2. Now, here's the thing. My velocity function, we actually might look at it as s prime sub t. It's the first derivative. But we typically like to say v sub t equals the derivative here. So 2 times negative 4.9 is negative 9.8t plus 18. That's velocity. Now, the acceleration function is s prime, second prime there, and it's the first derivative of velocity. So acceleration, that's how we might write it, is negative 9.8. Okay, now let's graph this function. So it's going to hit this y value. Here's 18, somewhere around there. This is 18, this is 0, 18. Okay, now it's going to hit the x-axis at that maximum. Remember, um, right here, v sub t equals 0. At this point here, so let's look about 1.75. So right about here, we're going to hit 0. And I can create my equation here. I can create it and make sure it goes through those points. Let's get this one coming right here. There we go. All right, so that's the equation of that. Now, how about acceleration? So at negative 9.8, right above negative 10, that's a negative 10 there. That's going to be my acceleration function. Okay, and you can notice when this is increasing, v sub t is positive. So v sub t is positive here, and it's negative right here. Okay, because this is always decreasing, its derivative, as you may have noticed, is always negative. So the rules still apply from some of the things we did with functions in the activity. So let's recall that when the derivative f prime of 0, f prime of x is less than 0, f of x is decreasing. Similarly, when f prime of x is greater than 0, f of x is increasing. And when f prime of x equals 0, f of x has a relative maximum or a minimum. Okay? So what does it mean in terms of particles, what they're doing? So that means for v sub t, this is s prime of t. How might we put into language of what the particle is doing? So if you keep it in mind, when it's negative, it's moving forward. So if you think about how it looks, what it looks like to you, visualize, this is the ball. It's right here. It goes in the air. Okay, that means it's moving up in this instance. When it stops, it peaks right here. It peaks. There's a peak, right? It's slowing down, and it stops. And then it turns back around and comes back down. All right? So it's moving forward. And then here, it means the particle is moving backwards. So it's not necessarily that we're talking about the particle itself and not the speed necessarily. So at rest, if you look at rest at this peak, at this maximum here, means the particle is at rest. And it's at rest because it stops moving for just an instant sometimes. And then it comes back down and it speeds back down, uses the gravity of the earth. And if that makes sense to you, it should make sense. I hope it makes sense to you. Anyways, average velocity is either positive or it's negative. Okay, average velocity is positive or it's negative. You could look at it as v sub 1 it's the average, so you just divide it by 2. The speed is always positive because it's the absolute value of the average velocity. So how about speeding up or slowing down? So what's happening if the velocity and acceleration have the same sign? The particle is speeding up. So let's go back and look at the graphs here. All right. So here, I'll tell you exactly where it's speeding up. The velocity has the same sign after it peaks down. So that means it's speeding up until it crashes into the earth. It crashes into the earth. Let me do that correctly because it's not quite there. It's like right here. It starts speeding up right about here. So from uh, 1.75 seconds till it stops, right? And that's only because of the impact of hitting Mr. Barua's hand. So if the velocity and acceleration are the same, opposite sign, the particle is slowing down. And obviously, when this guy throws it up into the air, it eventually slows down enough to stop and then come back uh, crashing to the earth. So let's draw some conclusions. Here, I'm just going to highlight the same signs here. These have the same signs, and these do. All right, but this velocity and this acceleration have opposite signs, so it's slowing down. This one has opposite signs, slowing down. This has opposite signs, speeding up, speeding up. When I do displacements, x sub t equals, let's go back to that velocity, 1/2 of v sub 1 v sub t sub 2, sorry, minus v sub t sub 1 times whatever the time is. So we need to write that in a different way, but we'll stick with that for right now. And this is basically what I'm trying to say is wherever we start this velocity, right, and wherever we end it at the end, that's what we're looking at there. Okay. And this t is just the time that it takes. It's just the time that it takes. So that's between, you could say t sub 2 minus t sub 1. Okay. All right, so just this one problem here, particle motion from an equation. This is the position of a particle moving on the x-axis is modeled by this function. So I'm just going to go ahead and get the derivative of that function, and keep in mind x prime sub t is the velocity function. So the velocity function is 3t squared minus 4 minus 8t, excuse me. Okay, the acceleration function, that's my derivative of the velocity there. So it's 9t, 6t. I don't know why I keep doing that. I keep seeing the squared, mess it up there. Let's erase a little bit there. That's kind of embarrassing. So let's try that again. 6t minus 8 is my acceleration function. So this is fine the displacement of the particle during the first 2 minutes. So that's pretty easy. This displacement is, I can just use, since this is the position where it's at. So they're just talking about, so x sub 2 minus where it's at, minus where it's at x sub 0. So it starts at 0, ends right here. We're not doing it in terms of velocity because we don't have to. So at 2, I have 8 minus 4 times 4 plus 3. I have that part. Okay, and then the second function, minus there. I wanted to emphasize that, right? Minus, let's go smaller. All right, velocity at 0. No, I'm talking about the position at 0, not the velocity. So 0 cubed minus 4 times 0 plus 3, and absolute value equals negative, okay, 8 minus 16 is negative 16 plus 3 minus 3. And I get negative 16, and I'm going to see what units we have here. Negative 16 centimeters. Just find the average velocity of the particle during the first 2 minutes. Average velocity, and I probably need to look at what I'm doing sometimes. All right, so v sub t plus v sub 1 over 2. Average velocity, so that's going to be v sub t sub 2 plus v sub t sub 1 over 2. And here I'm going to plug this in. Here's my velocity function, and I have to be really careful because sometimes I make mistakes when I get distracted, and that just happens. That just happens. So let's take our time, right? Plus 3 times 0 squared minus 8 times 0. Okay, and we get 9, no, 6, 12. 12 minus 8 over 2, and it's 6 over 4 over 2, messing this all up, and 2, and it's centimeters per second. Okay, let's find the velocity of particle when t equals 4. So I have my velocity function, v sub 4 equals 3 times 4 squared minus 8. This equals 48 minus 8, and that's going to give me 40 centimeters per second. Make sure that's right. That's the velocity function right there. I'm just going to erase this so it's a little bit neater, because I worry that when it's not neat, we make mistakes. And we want to focus on these things and be accurate. So it says find acceleration when t equals 4. So we have a sub 4, right? And here is the acceleration function, and it's 6 times 4 minus 8. That's 24 minus 8, and it's 16 centimeters per second squared. Okay? So just going back to this is a cubic function. Its derivative is a quadratic, and its derivative is a linear function. So is the particle speeding up or slowing down at t equals 4? So is it speeding up? So if it's speeding up, the signs are the same. So let's think about a statement. So the sign of velocity is positive, and the sign of acceleration is positive. These signs are the same. Therefore, the particle is speeding up. Okay. And that's all she wrote. Have a good day, guys. and I'll talk to you